Revolve is where things got started. It was my first combat robot as well as the subject of the first video on this channel. It's a 150-gram ring spinner type machine that is definitely the project I'm most proud of. The heavy ring spins around a fragile central robot. It is only one trick, but it's a pretty good trick. The final version recorded in the first video featured a successful implementation of a hub motor drive for the weapon, where magnets are embedded in the ring itself and spun by a sector stator mounted to the chassis. The final problem with that design was that the ring slowly expanded as fights went on, to eventually just pop off the bearings due to some inherent properties of aluminium and large centrifugal forces. With Robot Havoc 7 just a week away, it will mark 1 year since Revolve 3, so some upgrades are due. Revolve 3 had 3 significant problems. Firstly, the ring expanding and popping off the bearings. Secondly, the motor had unreliable starting at best. And finally, the shuffle pods were very time consuming to produce, with low usable yields from attempts. To address the first problem, we'll try to accommodate some ring expansion in the design. Fundamentally, there are 4 posts that constrain the ring. The concept will be as simple as featuring slots for 2 of said posts, and printing several blocks to push the bearings further and further out as needed during competition. This is much cheaper than having multiple sets of carbon fiber chassis parts. Unreliable motor start was presumably caused by a large gap between the stator and rotor, that is, the coils and the magnets. This mostly comes down to the assembly process, but the magnets will not be inset behind the protective epoxy as far, and the coils will be pushed out until the spinning ring just barely brushes past. As for the shuffle pods, printers have gotten more accurate and consistent in the 8 years since my Up Mini 2 was released. I fortunately upgraded to a Bamboo X1 carbon printer as first place winnings for a featherweight event, so we'll leverage its capabilities here, though any reasonably modern printer would have done the job just fine. Instead of 3 flattened paper clips to locate the shuffle cams at 120 degrees, I'll print a hexagonal feature that should easily align the parts for me. This should save some weight as well as a lot of assembly time. Generally, we're always gunning to reduce weight. The heavy metric 3 fasteners that the corner bearings run on will be replaced by 3mm carbon fiber rods, as well as generally replacing the excess carbon fiber sheeting with 3D prints. The robot frame will still be held rigidly with machined carbon fiber parts for stiffness, but I'll remove as much as I think I can get away with to substitute pretty colourful prints. The stator too will be thinned down by almost half as it's literally solid steel. Using the same piece of drone iron as last time, a section is hacksawed off, then the lamination split using a knife. Never before has robot weight loss been so easy. There's one final significant upgrade to Revolve, specifically the 2 large ring pieces. In the past, these were made of aluminium alloys, arriving at 70-75 as the best option. But this material creeps as the centrifugal forces pull outward, slowly expanding. Steel is not affected by this nearly as significantly, but there was no way I could manipulate the ring design to have weight for such a dense material, and practically machine the ring. So the only option was to pull one of the oldest robot builder tricks in the book. Stronger than aluminium, but lighter than steel, hide your engineering ineptitude under that pile of failed prints with titanium. At roughly 170% the strength of the best aluminium alloys, I designed a ring made of grade 5 titanium that is only a few grams heavier than the old one. Problematically though, this was not an easy part to machine. My mill is not equipped with flood cooling, and as such I have a small graveyard of end mills sacrificed to the high strength-to-weight ratio dice roll that is milling out small parts, let alone something this large. With that in mind, I would like to introduce PCBWay as this channel's first part sponsor, sparing me expansion of the cooked end mill pile. PCBWay offers several services, including PCB construction, regular and exotic 3D printing, and in my case a well-leveraged CNC machining service. They are only sponsoring the parts and their use, so I saw it fit to give the service an objective test. A step file for the part was uploaded to their website, as well as this drawing featuring no specified tolerances, to see what came out with their specified ISO 2768 tolerance standard. Once the parts arrived, I pored over them with my metrology tools. These results were fit into a spreadsheet and compared against the guaranteed tolerances. I was pleased to see that in every dimension it was well within tolerance, so full marks to PCBWay there. While intolerance and not intolerance should remain a Boolean statement, we can clearly see here that certain dimensions were extremely accurate, while others were more borderline. Perhaps a closer look at the parts may reveal why this is the case. The ring parts were designed to be CNC milled out of a cost-effective plate, as that's what the machine I have access to is best at. But a large manufacturer like PCBWay probably has better toys to play with, so let's see what clues we can uncover. Around the tool hard points are burrs that track with what I've experienced with milling, so this outer contour was likely formed by an end mill. This is backed up by the discrepancy in surface finish. One can see how deep one of the theoretical milling passes might have been. But more intriguingly is what lies inside, and on the back of the part. This inner corner has a slight radius to it, not what one would expect if this contour was formed by a sharp cornered end mill, but common to a lathe tool. That means this part was likely spun in a lathe at some point. The smoking gun here are these marks, distinctly telltale of a parting tool. What this means to me is that rather than machine this part from plate, they loaded a lathe with a monstrous titanium billet, at least 130mm in diameter, to do the high accuracy circular features. Then had the piece finished in a second setup on a milling machine, where the threads were also tapped. This may reveal a pattern in the tolerances, where the lathe features had a slightly different but consistent deviation to what I'm presuming were milled features in a secondary setup. I want to highlight how enormous of a chunk of titanium it must have been to make these rings, and how it's somewhat more cost effective for them to blast my parts out of that than mill it from plate. I of course might be mistaken with my detective work here, but it's fun to speculate. Back on track, we've got a robot to build. With the stated coil chunk cut to size, it gets coated in epoxy to keep the sharp edges from cutting into and shorting out on the coils. Afterwards, the coils are wound on by hand. These feature 20 turns per coil, all wound in the same direction as seen in CD-ROM motors. To refresh, my stator has 36 electrical poles and 48 simple magnetic poles, or a 3:4 ratio suited to this winding pattern. Another thing I want to highlight is that it's really not hard to wind your own motor, or at least a basic brushless one like we have here. It took me several versions of trial and error to improve my understanding of the theory, but now it's a pretty reliable process. Some general rules: you typically want to pick some wire that can roughly handle the target current, then pack as many neat windings onto the coils as possible. Building a motor for a target RPM or torque is very difficult. I actually have no idea what the specs of this one is, besides that it seems to work. There will be some links in the description with resources on motor construction if you want to try rolling your own. Next up is the rotor. I picked up a little bit of superglue to adhere all the magnets to a 3D printed retainer that will space the magnets in the ring before being permanently set in place with epoxy. Each of the 96 magnets has its polarity checked against a compass, then glued into place with this process taking about an hour. Noteworthy is that, like last time, a Holbach array arranges all the magnets to direct their fields inwards, as I've got no weight for a steel backing. I keep track of the intended magnet orientation by recessions modelled into the 3D print. While I don't know the true polarity of the magnets, all I care about is whichever face the compass faces north towards is set inwards on a high notch, and south facing is set inward on a low notch. I haven't figured out if a compass points towards magnetic north or not, but this seemed to work. Next is a lot of sanding. There is some variation in the heights of the magnets, meaning the ring halves don't clamp together nicely. Unfortunately, neodymium does not adhere well to the superglue, so they kept falling off. I give a few light scrapes on the sandpaper, replace the fallen magnets, then repeat. Sanding the magnet ring down to fit in the titanium rings took about 90 minutes. Next time I'll increase the space available in the ring to not require such high tolerances and save the trouble. When submitting the ring segment model for machining, I simplified it by removing the countersinks for the ring fasteners to make the part a single setup to reduce the cost. Leaving out secondary operations that you can do yourself is often a good idea. All this meant was that I had to machine those in myself, which was a very simple task using a 90-degree milling bit in a drill press. Finally, it was the moment of truth, to seal the ring parts together for all eternity with high-strength 24-hour araldite. Once it's mixed together, I have an hour to have everything assembled. Unlike previous rings, I used a 3D printed spacer to suspend the magnet ring in the perfect center and allow a smaller gap. Excess epoxy can be easily wiped away with a rag and some acetone, something I wish I knew when I built the first ring.
That's all.
With the ring freed, some magnets were sitting proud of the inner bearing race that had to be thinned out. After being marked, they were ground back using a Dremel. As found when sanding, neodymium produces lots of sparks when abraded, and it's definitely not the titanium. Finally, the magnets are coated with another layer of epoxy to seal them in for good. I'd warn against trying to file the magnets as they're prone to cracking. With faith in the mechanics, the robot needed some wiring. It's a simple transplant of the old robot electronics into the new, besides some more powerful drive motors. With the robot theoretically functional, it's time for the first test. It's pretty high stakes. If any of those 96 magnets was flipped by accident, then the weapon simply wouldn't work. Bonus points for being unable to tell which magnet was wrongly placed anyway. Even more bonus points, being set in epoxy, I couldn't remove them from the rotor if I tried. Nonetheless, with a fully charged battery, the robot was set down and throttled up. Looks like it works. This wasn't the first attempt though. I've got some telling slow motion footage here showing some failed starts. You can actually see the individual pulses the motor controller gives to the coils to try and start the motor, including a half start. Noticeably absent from any of that footage is the robot actually walking. With the newfangled printer, I had been printing innumerous failed shuffle pod prototypes when assembling the ring. The hexagonal locators worked well, but I just couldn't get the shuffle pods to do even a half turn before binding. I tried both PLA and ABS, loose and tight fits on the cams. The old shuffle pods are very poorly made, and yet worked fine. I was pretty baffled. Eventually, I had a bit of a eureka moment and realised I had months ago reduced the eccentricity of the cams when mocking up the new robot. I increased the offset by 0.5 mm and it instantly worked. All that effort and time for such a simple mistake. With the walkers working, we get the first combination working footage. I now know that my phone's ultra slow motion doesn't record sound, but seeing things at such a rate is pretty neat. I was then able to reduce the gap between the stator and magnets, but immediately had to pack up and trip out for a local Antweight event. Adelaide is the big game we're practicing for, but this smaller competition should help iron out any bugs in the design.
3, 2, 1, go! Yes. That way. That's a drive side slightly messed up. Yes. The forks. No. Think will help you. Oh, with a pin.
A good showing from Revolve, winning all of its fights but not unscathed. Revolve last fought almost a year ago, and a key development since then is the proliferation of TPU chassis, which are very resilient to relatively low speed impacts. Both Hexwitch and Yellow and Dangerous are constructed this way, and as such took the hits very well, though eventually failing to the onslaught. I am happy to report that the ring never failed to start smoothly, which is a massive upgrade over the previous version. In the final fight, a rematch against Yellow and Dangerous, we both spun our hardened steel weapons up to maximum speed for the first time before connecting. It may seem like a relatively small hit in the video, but it was far from it. I dare to say that it was the most energetic Antweight interaction I've ever seen. As for my opponent, the hit sheared the top shaft of the weapon and shattered the magnets in the motor, leading to excessive drag and the preemptive shutdown. Revolve's tooth broke clean off, with the metric 3 fasteners failing in double shear. According to literature, each fastener fails in that way with applied load of 3.96 kilonewtons. Therefore, with spherical cowls and slimbified mats, there was an instant where more than 385 kilograms of force was applied to that tooth. It was likely less for a variety of factors, but even a tenth of that is more than one would expect from a 150-gram robot. The ring even punched an indent in the titanium ring and almost dislodged the magnets. Nonetheless, Revolve will be repaired for Adelaide, though I don't have time to improve the ring hardpoint design. But a question remains. Ring spinners have and always will be expensive, time-consuming, and maintenance-heavy archetype, so why continue developing this one when there are far more competitive and, dare I say, fun designs to fight with? I don't have a great answer, but it's probably something to do with seeking a challenge. It also stands as a testament that Split got one version and never touched again, whereas Revolve is 4 deep with more to come. As difficult as ring spinners may be, it ends up being worthwhile for shots like this. Until next time.